Till now we have learnt that for estimation of parameters which involves complex mathematical forms, we can use resampling techniques like the jackknife and bootstrap. We have seen a couple of examples where we can use bootstrap to good effect to find the sampling distribution of the statistic as well as an estimate of the variance of the statistic. In today's session, we would be learning about the bootstrap confidence intervals. So, we would start with a general recapitulation of the confidence interval in itself, and then we would see that there are different forms or variants of bootstrap based confidence interval like the bootstrap T, the bootstrap percentile, the bootstrap bias corrected confidence intervals, the bootstrap bias corrected accelerated confidence intervals. So, we shall investigate all of them and see what is the difference between each of them and how we can construct them. Now, let x1, x2, xn be IID random vectors from an unknown f, and let theta is equal to t of f be a parameter of interest. Assume Cn is equal to Cn x1 dot xn is a subset of R such that probability theta belongs to Cn is greater than equal to 1 minus alpha. Cn is called a confidence set for theta with level 1 minus alpha. The factor 1 minus alpha, which is the probability, is called the coverage probability of Cn. If the strict equality holds, then Cn is a confidence set with confidence coefficients 1 minus alpha. Alternatively, we call Cn as a 1 minus alpha confidence set. Now, let theta underscore is equal to theta underscore n x1 to xn and theta bar is theta bar n x1 to xn. Then minus infinity to theta bar and in theta bar to infinity, left open, right closed in both are called one-sided confidence intervals, whereas theta under bar and theta bar is called a two-sided confidence interval. Now, how are the confidence intervals or the confidence sets constructed? Confidence sets are usually constructed by considering a pivotal quantity Rn, which is equal to Rn x1 to xn and f. So, Rn is based on the samples and f, whose distribution is assumed to be Gn and Gn is independent of f. Example, if Rn is theta n hat minus theta by sigma n hat, which is variance of theta n hat, then the exact 1 minus alpha percent confidence interval for theta is theta n hat minus sigma n hat Gn inverse 1 minus alpha by 2 theta n hat minus sigma n hat Gn inverse alpha by 2. Now, the main disadvantage here is that Gn or any of the limit needs to be derived analytically and explicitly, whereas for a bootstrap confidence sets this can be derived computationally. Now, let us consider the first type of confidence sets, which is the bootstrap T. Note that because the confidence interval for the upper and the lower limits are similar, we would be illustrating the lower limit only. The upper limit is like the minus sign would be changed to the plus sign. So, we would see what happens when we come to that. Let us go into the bootstrap T confidence intervals. So, define the pivot Rn is equal to theta n hat minus theta by sigma n hat. The distribution of G, the distribution G of Rn is unknown. Then it can be estimated by the bootstrap estimator G boot x, which is P star Rn star less than equal to x, where Rn star is theta n hat star minus theta n hat by sigma n hat. So, the lower confidence bootstrap limit for theta would be theta bt under bar is theta n hat minus sigma n hat g boot inverse 1 minus alpha, and for the upper it would be theta bar bt, which is theta n hat plus sigma n hat g boot inverse alpha. So, inference for location parameters, suppose x1 to xn is IIDF and let theta is equal to expectation of xi, then Rn would be xn bar minus theta by Sn, where Sn square is sigma hat square by n, where sigma hat square is the sample variance. Now, if fx is f naught x minus theta by sigma, then the distribution of Rn will not depend on f. If f naught is known, the bootstrap approach will be the same as the traditional approach. But if f naught is unknown, then numerical computations will be required to obtain the bootstrap approximation of f naught. So, for the non-parametric cases, the bootstrap tree would involve generating bootstrap datasets from the empirical distribution of fn hat and calculating g boot inverse 1 minus alpha. So, instead of the true alpha, so the advantages for the bootstrap tree method is that the bootstrap tree method is simple and easy to understand. The confidence bound theta under bar bt can be shown to be highly accurate, but there are disadvantages, and the disadvantage is that we need a variance estimator sigma hat n square. If no other estimator is available, then we can always use the bootstrap variance estimator V boot. But however, if G boot and V boot have to be approximated, we need to do nested bootstrap. That is, for each sequence of V bootstrap datasets, we need to approximate G boot, we generate B2 bootstrap datasets to approximate V boot. So, for the first, we first generate B1 bootstrap datasets to approximate G boot, and then we need to generate another B2 bootstrap datasets to approximate the V boot. So, that means we are nesting the bootstrap technique here. Also, the bootstrap method is not invariant under reparameterization. So, if we reparameterize, then the confidence interval is not invariant. The bootstrap percentile. Here, assume that theta n hat is the estimator of theta and theta n hat star is the bootstrap estimator based on x1 star to xn star, or the bootstrap sample, and define k boot x is p under the bootstraps, that star theta n star hat less than equal to x. Now, the bootstrap estimate percentile method gives that theta under bar b, the bootstrap percentile is k boot inverse alpha, or a percentile of the bootstrap distribution k boot. Let us take an example. Suppose x1 to xn follows IIDF and theta is equal to median f. Let theta n hat is xm, or the middlemost order statistics, and theta n hat star is xm star, and it takes the values x1 to xn with probabilities given by p star. Xm star is equal to x order statistic k given x1 to xn, which is nothing but j runs from 0 to m minus 1 mcj k minus 1 to the power j n minus k plus 1 to the power m minus j minus k to the power j m minus k to the power n minus j divided by n to the power n. Therefore, theta under hat bp is x k tilde at the top. So, that is the order statistics, where k tilde is the smallest case such that j runs from m to n, n c j k to the power j n minus k to the power n minus j by n to the power n is greater than equal to alpha. Now, the bootstrap bias corrected percentile. Now, suppose there exists a transformation such that p of phi n hat minus phi n theta less than equal to x is equal to psi x for all f, where phi n hat is phi n theta to the power n hat, and psi is continuous and symmetric with increasing. Example, psi can be capital phi, where capital phi is the normalizing and variance stabilizing transformation. Now, if psi n and psi are known, then theta exact is equal to phi n inverse phi n hat plus psi inverse alpha. If psi n and phi are unknown, then let W n is phi n theta underscore B p minus psi n hat. So, since the first inequality, that is probability of phi n hat minus phi n theta less than equal to x is equal to psi x, holds for f at n also. So, psi W n is p star phi n star hat minus phi n hat less than equal to W n is equal to theta n star less than equal to theta B p, which is equal to alpha, which implies W n is psi inverse alpha and theta, the lower bound, that is theta lower bar B p or under bar B p is psi n minus 1 phi n inverse phi n hat plus psi inverse alpha, which is equal to theta exact. However, if psi is non-linear, then the probability in 1 holds only for larger samples, and phi n hat minus phi n theta will be biased in small samples. So, this means that we need to accommodate a bias term, and that is the reason we go into the next, which is bootstrap bias corrected percentile. So, here probability of phi n hat minus phi n theta plus xi naught is less than equal to x is psi bar x or psi x, where xi naught is constant that may the bootstrap bias corrected percentile. Now, to adjust for that bias, we can consider a more general assumption, which is probability of phi n hat minus phi n theta plus xi naught less than equal to x is psi x, where psi naught is a constant that may depend on f and n. Now, if we assume f equal to f hat, we get k boot theta n is p star phi n star minus phi n hat star minus phi n hat plus xi naught less than equal to xi naught is psi xi naught, where p star is p star theta n hat less than theta n hat star less than theta n. Xi naught then comes out to be psi inverse k boot theta n hat. Also, from this basic equation, we can say that is the first equation, that is psi n hat minus phi n theta plus z naught less than equal to x, the probability of it is equal to psi x. We can say that 1 minus alpha is psi minus z alpha. From there, we can, with some algebra, we can reach the step which is k boot inverse x is phi n inverse phi n hat plus psi inverse x minus z naught. So, theta under bar exact, so that the exact lower confidence interval comes out to be k inverse boot psi of xi alpha plus twice xi naught. So, the lower bound comes out to be k boot inverse psi of z alpha plus twice psi inverse k boot theta n hat. Usually, we can use psi to be equal to capital phi. So, if we use psi, and since psi inverse half is equal to 0, theta under bar the bias corrected lower bound is equal to the lower bound of bootstrap percentile if k boot theta n hat is approximately equal to half. That is, if theta n hat is the median of the bootstrap distribution. Thus, the lower bound for the bootstrap corrected confidence for the bias corrected bootstrap confidence interval, that is theta under bar BC, is a bias adjusted version of the bootstrap percentile. There are further versions of this, which is called the bootstrap accelerated bias corrected percentile, and the hybrid bootstrap. So, we are not discussing those, but the lecture notes contain the details of the bootstrap accelerated bias corrected percentile and the hybrid bootstrap. In this session, we learnt about the various bootstrap confidence intervals that can be performed or computed using a bootstrap sample. So, we can have the bootstrap T confidence interval and the bootstrap percentile confidence interval and variants of bootstrap bias corrected confidence intervals. So, the way bootstrap T confidence interval is exactly like the ordinary confidence interval, but using the bootstrap distribution, and the bootstrap percentile confidence and the bootstrap bias corrected confidence intervals are other variants of bootstrap confidence intervals that can be based solely on the bootstrap samples. In the next session, we shall be talking about the different computational issues that are associated with bootstrap samples.